We're Team 15, and we did the upright robot.
The purpose of this project is to build an upright robot, and it must stand for at least 10 seconds. The motor driver uses corrective action to keep the robot upright. For the design of the robot, we went through different iterations of the frame. For the sensor, we used a digital accelerometer and gyroscope combo. We then tested the open loop system with changes to the controller design, and then we demonstrated the working closed loop system of the upright robot. For stability, we needed closed loop poles in the left half plane. We also need to be near critically damped to get the fastest response time, but not to have overshoot of an underdamped system. If there was an overshoot, however, the system will oscillate back and forth, causing increased instability. We will aim to create an overall transfer function with two real values, repeated poles.
So for the major components of our prototype, we had the big robot body, which we had 2 iterations of. This is our final one. We had 2 6-volt motors on the bottom. You can't see it, but they're attached to the wheels on the bottom of the frame. Brackets for the motors. Then we had 2 wheels. We had the screw hubs for the wheels. Then we had a H-bridge motor driver, which is the red box right in the middle there on the bottom of the robot. Then we had the sensor, which was the accelerator gyroscope combo on the top, which was the red square up there. And then we had the Arduino microcontroller, which is the big blue square right in the middle. And then we had 2 9-volts, and we had 2 potentiometers on the breadboard on the bottom of the screen, which helped us adjust our controller values. So for a controller, we initially solved transfer functions and used a Routh array to determine a proper range for stabilization. And then we simulated our system in Xcos to simulate the KP, KI, and KD values, and had various plots and stuff to optimize them. Then we wrote the Arduino code using a theoretical design of the controller to test and apply troubleshoot methods, and we were continuously editing the code throughout this for optimization. And then we used our code, and our robot was correctly responding to it. When it was falling forwards, the motor was driving the wheels forwards. When it was falling backwards, the motor was driving the wheel backwards, both to correct the motion and bring it back to 0 where the motor wouldn't run. Then we added potentiometers to the system, which allowed for quick and manual adjustments to the controller values instead of having to reprogram the Arduino every single time. And then we just kept using a trial and error method by modifying the KP and KD values to force the robot into stability.
So this is the Arduino code we used. On the left is actually the first part of the code, where we start by initializing the libraries of the sensor and initializing our variables. We then set the pin mode of the pins on the Arduino as outputs. That way we can write to the motors through the motor driver. We then calculate the time of the loop, which is going to be used later in our theta dot calculation. Then below the time, we read from the sensor the x theta value, and then we calculate x theta dot by subtracting the previous value from the current value and then dividing by the time we calculated earlier. On the right side is where we analog read the potentiometers to write to KP and KD. Those values are scaled based on those readings. We then calculate our corrective action, epsilon. The next part of the code is to set the saturation point, because the motors can only be written to such a high value, and for ours that value is 255. The final part of the code is the if statements to determine if the robot is falling one way or the other, and then write to the correct motors to correct that.
And then as he
KP
turns
0.
it,
Crank up KP and get stop, falls back, falls forward. Crank up KP, the speed increases.
reading from potentiometer. I don't know. We need to do that. It maxes out. That's as high as KP goes. KP and still. Motors aren't rated for 18 volts, and they're drawing way too much current. Pull it away from the Arduino. I wonder what will happen if I invert. Invert this one.
If we were to do this project all over again, there are a number of improvements we could have made. Our success and failure hinged on the speed of the Arduino loop, and we found that by deleting the serial print function, we were able to cut loop time by a factor of 10. Additionally, our sensor choice required the use of an external library that required excess time in order to access the values of x theta. We found that our motors were rated for a much smaller voltage than we supplied, and therefore they drew too much current and pulled too much current away from the Arduino, which caused it to reset, increasing our loop time as well. Another mistake we made was designing the robot on the presumption that we'd be able to power it with two 9-volt alkaline batteries. We found that these batteries are both limited in their capacity and current draw, which prevented long periods of testing. In the future, a higher capacity lithium battery would be much more useful. Also in the future, we would, if we had more time, we would incorporate a KI component, as stability can be reached with just KP and KD, but long-term stability is dependent on an integral component.